Hey everybody, Blake Veneer here again with another part in my series where we're talking about spacetime particles, which is an Aether model that will hopefully help us answer some of the unresolved issues in physics, such as dark matter. And in this part, we're going to talk about how gravity does not bend light. So, what we will cover, it's all about light and spacetime. So, and there's some random tangents, but we'll just get into it. Now, the first question I've always wondered is, does light bend space-time? Now, general relativity would say that light has energy and momentum, so it does contribute to the stress energy tensor. So I guess the answer's yes. Another expert could perhaps answer that in general relativity, but in order for gravity to be a thing, it has to emit, well, at least in the standard model, they would say that it emits, gravity is um, mediated through gravitons. So does that mean light emits gravitons? I don't know. So um, let's pretend we had a bagillion watt laser, and that's just some laser that is incredibly unrealistic and technical term, I'm pretty sure. We have this laser here, my standard laser emblem, and it is shooting a huge pulse of energy. And we're just going to say that this is 1 second for some reason. I don't know if it matters. This is a big photon. And the energy is equivalent to, this would be 1 Earth mass, right? So it is an ungodly amount of energy. Now we're going to put one person very far away. This doesn't really matter. I just know that generating a pulse of light this large would certainly change the mass of whatever is doing the generating, and I want to be far enough away from that this person is kind of immune. Not immune, but they certainly would feel it as a ripple, but it would be a small ripple. Now, my question is, I don't know why this would be something, this distance is a reasonable amount of distance, right? Maybe radius of Earth. I don't know. Let's do that. So the question is, as this big thing goes by, will our person feel that force or a gravitational force or acceleration, whatever you want to call it? Now, one weird thing is if you look at a photon, I guess they're red today, it is moving at c. And if it's emitting gravitons, like, how are these gravitons, are they just emitted outward? Like, typically, we would have a relativistic aberration for something like this, but that is for when velocity is less. Boy, that's really bad. You know, relativistic aberrations are for velocities less than c. So how do you, what is the direction or the like of a graviton that's emitted from something moving at light speed already? Typically this, you know, your relativistic aberrations are let's change this to for a mass moving. So if you have, light being emitted all the way around, we have velocity equals something, I don't know why. Then this light is going to be focused in the direction of motion. I don't know how that happens with something that's moving at sea. So there's my question, and somebody else can try to answer them if it's really interesting. So my general thought would be that light does not bend space and time, even though that's against kind of, it might ripple, it might distort it a little bit, but I guess what I'm saying is that light does not create a gravitational attraction of mass. Because really that's what gravity is. Gravity is an attraction between masses, and photons don't have mass. So let's look at the density of spacetime. So I would argue that spacetime is made up of spacetime particles, and without any outside influences, the spacetime particles are going to be nice, like mostly uniformly distributed. So there might be oscillations and weird fluctuations, but generally you're going to be able to say that there's a uniform density of the spacetime particles. And I am always going to call that rho naught. Now, the interesting thing here is somebody would say, well, then that means that everything, even empty space, contains mass, right? So you'd take a circle or a sphere and you'd be able to say, hey, there's mass in that sphere. But we don't see that. Well, what I'm saying is that it's kind of like atmospheric pressure. Even though the atmospheric pressure around us is pretty significant, we don't feel it because it is all around us. It is only when you create a pressure difference that you can appreciate how much one atmosphere is actually pushing. So let's imagine that we take some energy and we start pushing these space-time particles together, and we make a concentration. And let's just say the amount of energy we use is equal to something random. I don't know. But I would argue that once we create a concentration that is different than the surrounding, that's what we would see as mass. That's a pressure difference, so to speak, with our analogy of pressure on Earth. And so if we were to look at that, I would argue, additionally, here's my R, this is going to be rho. I'm going to say that our density here of around a mass, and our density here far away, I guess it could fall off sharply, but realistically, I think it's going to could be very sharp at the beginning, but it's going to be smooth here. And maybe there's some sort of step at the very, very edge. But what I'm saying is that I think that as you create a density, increase in density, the rest of space-time particles around, a particle or a mass is going to be pulled in a little bit, so the density around mass is going to be higher than far away. So that's an assumption. Again, I guess people could argue that either way. Okay, so let's look at these two different situations where we have two different densities of space-time particles. And we're going to call this observer 1, rho, and that's going to be equal to n times some rho naught is just the the background or some empty space reference, and then observer 2 is going to be rho n naught. This is going to be 2 2 1 1. And what I am postulating is that the speed of light for both of these frames is going to be the same. First, let me define this new metric. So this is going to be distance, and this is going to be distance. Now I'm defining this new metric, and that's going to be D12. And essentially that is saying in frame 1, looking at frame 2. Now, when we are comparing the two frames, we can't actually, observer 1 can't actually measure or do anything in observer 2's frame without actually being there. So we're going to kind of do all of this in this imaginary kind of space. So let's look at this. So the speed of light in frame 1, looking at frame 1, is going to be equal to c, and that's going to be equal to d over t, and to be more specific, that's going to be d11 over t11. So that's the speed of light in its own frame is going to be moving at distance divided by time in that frame. And the same thing over here, c22 is going to be equal to c as seen in that frame, d over t, same thing, 22 over t22. Now, we want to compare d11 and d22. And so we have to kind of establish this imaginary, the comparison. And I don't know why I'm going to do it over here, but when we're looking at the two, it is, as I said before, we're going to be comparing d12, so that's the distance in frame 1 looking at frame 2, and d21, same thing. Distance from frame 2 looking at frame 1. And so you can imagine when the density is different, if d1 is something looking like that, d2 is probably, it's going to have like twice as many if the the ratio of n1, n2, or n2 to n1 is about 2. But basically, I don't know if this is like a proof or if we can just accept this relationship, but the relationship that I'm proposing is that d12 times n1 equals d21 times n2. And just for simplicity's sake, because we really only care about the ratio between the two, I'm going to define 1, 2 is equal to n2 over n1. That's just typically because we are looking at higher densities, and so I flipped it upside down. I don't know. So this is, and this is roughly n equals 1, 2 equals 2, right? So you can tell that it's about twice as much. And this is kind of an imaginary space. Is that actual? Does it matter that I'm mentioning that? I don't know. It's just, it's more important when we look at time. But now, when we look at T12, that is going to be D12 divided by C11. And this is assuming we are picking the frame of observer 1 as our reference frame. And why is that important? Well, if we pick observer 1 as our reference frame, D12 is equal to D11. And the important thing is that T12 is equal to T11, right? So we're just saying we're looking, the most important frame right now is our observer 1. And so we have this relationship. And what does that mean for 2? That means that D21 is still, that still holds because we have this relationship I circled in blue. However, this is not necessarily true anymore. We don't know what that is. We don't have a relationship yet. So, let's see. And so this is going to be now. What does, so, and that does, that's ultimately just C, right? So what do we want to, so the next thing that we're interested in is T of time T, time from frame 2 looking at frame 1. And we're going to do the same sort of thing. So D21, and this is going to be C22. Okay. And then we can use this relationship in the blue to calculate D21, which is now going to be okay, so I took the C22 as just the speed of light. Now we want to do a ratio. Now I'm curious about how the two times flow with respect to each other or relative to each other. So we're going to do a ratio. And so that's just D12 divided by C. And then we have D12 divided by N12 divided by C. So we can do some cancellations, right? And essentially that's 1 over 1 over N, 1 over 1 over N1, N12, which is essentially N12. And so the next step we could do is 1, 2 equals, right? So when N is greater than 1, time is going to move slower for frame 2. So in frame 2's frame with higher density, it's going to look like time slowing down because more time is going to pass in frame 1. And then let's just finalize this. So T12, remember N12 is N2 over on top, T21. So this is our other equation. Okay, now what does the speed of light look like? So we can't actually measure the speed of light in another frame because we're not in that frame. But we can make some assumptions of how fast that speed of light would be going, or how fast, if we were to send signals of the speed, we can make it, infer how fast it's moving that way. So I'm wondering, what is the speed of light from frame 1 looking at frame 2? And so we are in frame 1's reference frame. And so I'm interested in frame 1's distance. And we are interested in the time it takes with respect to frame 2, though. And remember, we can simplify this. We know d12 is really just equal to d, so we got t over. Now, so this is frame 1. Now from frame 2, time 2, 1, is the distance that we cover, d12, by the speed of light in that frame. So it's just our c22. We know the conversion for d12 to get it in d21 frame. I just dropped the 22 because we know that that's equal to c. And so to finalize that, well, and then again, remember d21 is just equal to d. So we got essentially d1 d over c. Now we're going to plug this in. Well, I guess this one or that one, whichever one. So C12 is equal to D over N12 times D over C. Again, we have a weird 1 over C, but we're going to cancel the D's. And this is going to look like C over N12. So as N gets larger, the ratio between, as the density ratio grows, C, our speed of light, the apparent speed of light is going to decrease. Let me write these out fully. And so what we're looking at is C12 times N12 equals C. And conversely, C21 times N21 is also equal to C. If we want to just simplify it a little bit more, okay. Okay, so those are relationships when we're looking from one frame to the other that has different densities of space-time. And now I am suggesting that speed of light is going slower in a different frame, and that might freak some people out, but let's look at that. Now, having the speed of light differ in different frames is actually nothing new, and we can look at general relativity as an example so that this might be less freaky for everybody else. And this is just another one thing, like something that I had to kind of realize in my physics journey, is that it's like I always imagine that you would look on the surface of a black hole and you'd always see light moving at c. You'd always see light moving at c. It's funny. You'd always observe light moving at c. And that's not actually the case. So let's do an example. I don't like to talk about black holes much because I think it's too extreme for what we're capable of, but let's just assume here that we have a black hole and it's black, conveniently. And we're going to have a track, not a track, but So this circumference is going to be the photosphere. That's a location where light, if you shoot light perpendicular, it is going to just basically orbit. So along this photosphere, we have our laser that shoots light that way. And then we have these little ground station, photosphere stations. And perfectly, directly above this black hole, we're going to have a person. And this is going to be some huge distance. And we're going to be beaming time signals. I guess we need another. That one. So we're beaming directly above the black hole, and each path that we're taking is going to be the same as all the others, so we can expect that any time dilation or deviations of the path is all going to have the same compensation. So one thing that general relativity says is that the circumference we'll just say here is this is observer 1 and this is observer 2. So the circumference is not changed relative to the two frames. So we can agree on that. Now, observer 2 is going to shoot this light out, and they're going to see it race around the circumference. And they can measure the time, right? So C observer 2 is going to be equal to and that's going to be equal to C. They're in this frame. They're going to measure the speed of light moving at C because the potential does not change along the photosphere, and so they are going to get C. However, we know from general relativity that there's time dilation as we get closer to a massive object, and so the time 2 is going to be less than time 1, right? So we'll measure 1 second. I guess there's going to be some correction factor. Well, so really it's going to be and so as gamma grows, and this is actually a pretty, I'm sure there's an easy calculation to calculate gamma right at the photosphere, but I do not have it on hand at the moment. But yeah, as I was saying, so if gamma gets larger, then T2 has to decrease. And so less time passes the closer you get. And so with that in mind, T1, 2, this would be 2, 2, is going to be the same circumference. And so T1 is larger than T2, and so therefore the bottom gets bigger, the top gets, so the overall value gets smaller. So this is just an inferred speed of light because, again, we can't actually measure this. So we would see as light moves around this photosphere, we could say our ground or our photosphere stations would emit timing signals, and they would measure, this is how you'd visualize light moving around, but there'd be a delay between each one of these signals. and you could relate that to a decrease in the speed of light, an apparent speed of light. So here's my little tangent I promised, and we're just going to be talking about time and materials. And the goal of this is just to get, to the topic of if gravity doesn't bend light, what bends light? Okay, this is probably the biggest tangent of the entire thing. So time, and my point here is that time flows for a photon. People like to say that time dilation, as you go faster and faster, time goes slower and slower. And so for a photon moving at light speed, your time dilation would be humongous, and so therefore no time passes, right? So a photon basically is frozen in time. However, time dilation is related to moving mass. It doesn't apply to massless photons. The photon only cares about the dominant inertial sphere it is currently traveling through, so its frequency is tied to that frame. That frequency is like its heartbeat and describes how it evolves over time. So what does this mean? So if we have this spacecraft moving through, a relatively like still medium of space-time particles, it is going to generate its own little inertial sphere that we talked about in the previous episode. Now, with red light, and we're going to do just Einstein's experiment. So light is shot and bounced off a couple mirrors. Now, what I'm arguing is that the person on this spacecraft is going to say the length of the photon is equal to n periods. So just depending on how, the big spacing, but they're going to say the light traveled 100 periods or 1,000 periods to get there and back off the mirror. And this is right, because this whole inertial sphere is moving along with the spacecraft. It's kind of locked to the spacecraft. Now, a stationary observer is going to also measure. They're also, the light, the number of periods is not going to change just because you're looking. The distance and stuff is going to contort. They're going to say that the spacecraft looks at a slightly different side. Speed of light's going to be moving slower, but fundamentally, the same number of periods are going to occur for both observers, right? So they're going to see light with a slower, basically a heartbeat, as I was saying, a lower frequency, because it's in a moving frame, and that time dilation applies to the photon in this frame too. Now, if we have this photon moving out, boy, maybe this should be, I don't know. Maybe the photon goes here and gets deflected this way. And let's just imagine that the observer is over here. But from this point, the photon is now in the stationary frame. it's going to have some frequency changes and energy changes because it's moving from the two different frames. But ultimately, now there's going to be no time dilation as seen from the stationary observer. This is just kind of a weird random thing, but I do like to think of photons having kind of this heartbeat, and that heartbeat is tied to the frame that they're moving through. Random, but maybe just interesting enough to leave it in here. Now, light in materials. This sounds like we're on a massive tangent, but I promise this will make sense. So in modern physics, the explanation here is, let's just say we have n equals 1, n equals 2. As light moves through a medium of higher index of refraction, so glass or water or whatever, I guess I said 2 would be diamond. I think it's 2.4, but don't quote me. As light moves into a material with higher index of refraction, it slows down. And the explanation here is that we have light moving this way. It goes in to this new material, no problem. However, the electrons the electron response of the material kind of moves in the opposite direction, or as like a retarding field. And so what we actually see is gamma with n2, which is less than c. So this is the explanation of modern physics. I think it's a little bit hand wavy, but probably a lot of people are going to look at everything I'm doing and say that's hand wavy. So we could call it even. But anyway, this is the general explanation. Hopefully I got that right. Now what I'm proposing is that light is an oscillation through space-time particles. An electron is space-time particles in a different configuration or concentration. Glass or water or diamond or whatever is just a lattice of atoms that fixes electrons in place. A fixed grid of electrons is essentially a medium for light to travel with different properties. The space that this medium occupies could have a higher density of space-time particles, so therefore light moves slower. Just to clarify here is that the full volume that the electrons, the allowable space that light's moving through in this lattice might not be equal to the volume of the medium. Like there might be some, the electrons could provide restricted pathways, which helps to boost the density or something higher. But it's certainly not necessarily going to be the volume of the water is equal to this mirrored out, all of the space that light can move through. I don't know if that makes sense. But now the new medium is restricted to the characteristics of the atomic lattice. So if you add too much energy, then you're going to break this lattice of electrons and you're going to eject an electron. And so the electrons in this lattice can only move so fast to respond to the photons moving through it. And so that's why we see the speed of light vary for different wavelengths. Now, space-time particles in vacuum don't have these restrictions, so all wavelengths travel at c. In most normal cases, I don't know, it's so easy to extrapolate to high densities or the entire universe, but I'm saying for most of the cases that we can experience, I don't expect that there would be a different speed of light for different wavelengths or different energies of photons. So, what if the density of spacetime particles is what guides light? And which is totally independent of, the force of the acceleration generated between two bodies of mass. another little detail or distraction tangent. General relativity is going to say that space-time is stretched. This is a black something of high mass. So space-time, maybe that's one word. Let's make this more extreme. Now, one thing to note is if you're a person at this location, general relativity says that space-time is a non-Euclidean geometry. So a Euclidean geometry is where 2 pi r equals the circumference, right? So that's what we would expect. If the blue person over here can measure their circumference, then they can measure r here. However, if they drop a rope, let's go red, a rope down here, the length of the rope is going to be greater than r because space-time is stretched. Now, what does that look for a meter stick? Let's just say we have a meter stick of uniform length. The meter stick, nothing goes wrong with the meter stick as it enters, but from an observer high or in a normal reference frame, oh, that should have been smaller. The apparent length is going to be, whoops, so far away, you're going to say 1 meter, but here, this is going to be less than 1 meter. Right, so as the meter stick moves into closer to the gravitational well, it's going to look like it gets shorter and shorter. So what does it mean? Like, how does this even make sense though? Right? What does it mean? And so that's my big question, right? But what if it's not stretched? What if that's just the weird, maybe it was just the wrong kind of intuitive leap there. So our earlier discussion, we said that far away from any mass, you're going to have some default density. Now, close in to this mass, you're going to have a high, a density that is much larger than, this must be a really dense object if it's much double greater than. And so the density is here, and I also argued that the density is going to change, not necessarily, smooth, well, it'll be smooth, but just it could be very sharp here. I guess that should have approached. Let's try that again. Closer. Now, imagine if instead of space-time being stretched, it's really just a higher concentration of space-time. Whoops. Jeez Louise. Clearly did not get good grades in art classes. So what if we view space-time as not being stretched, but just being higher densities? So if we have a meter stick, what does that look like? Well, it turns out as the meter stick goes into higher densities, it's going to have the same I'm not going to do all these, but you can get the idea. 1 meter, and this is going to be, you know, really bad. So if you look at spacetime as being a higher concentration, it's the same result, just with a different view. And to me, having a higher concentration of spacetime seems to make a lot more sense than if spacetime is just getting stretched and pulled apart. Now, what does that look like here? Again, if we have this giant black dot with some unknown mass, and we have our fancy laser. Well, so we're going to have high. Whoops, man, why do I keep doing that? Here. So basically, then this means, let's just assume n equals 1 here, n equals something, just say greater than 1. And so as light moves, as this line of light goes towards this higher n value, it's going to want to pull, man, right through the, right? It's going to guide the light around just like you would see in glass or in a prism, right? So n1, n equals 2. As light goes into water, as light goes in at an angle, it's going to get bent. And so again, the same thing here. As light goes towards the higher n, it's going to be kind of pulled along the higher density of space-time particles. So, and what's the main big point here is I am pretty confident that light, or I feel strongly that light doesn't have to have, doesn't have to interact in the same way as mass does in order to still have the bending that we'd predict in general relativity. Let's just look at this example here. Oh, why didn't that work? Now, just on a side note, if you look at from above, energy of, let's just say we have some energy of a photon is equal to hc lambda, right? We just go like that. Now, if we look at energy of the same photon, well, it's just repeating myself, but so let's just say we have the same photon being emitted from two different reference frames. So we can drop, right? So this gets dropped, this gets dropped, this gets dropped, that gets dropped. So looking at the energy from frame 1 into frame 2, we're going to see right, so this is going to be the speed of light divided by your, the speed of light of C12 is going to be smaller. So it's going to be divided, I guess it depends on the ratio, but I've always been treating N2 having a higher density. And the length is also going to be shrunk, right? But lambda 2, 1 equals lambda. And so really, Basically, as you look at the same photon from every reference frame, they're going to have the same energies, right? Because these get canceled. However, what happens, that doesn't actually account for photons moving through from one frame to the other. Now, what I'm going to say here is that a photon exists over time. In order for light to travel between two different densities or two different frames, time must be conserved, or basically the photons between the two frames must so the photon has to, from frame 1 to 2, has to interact or transfer over the same amount of time from respect from both sides. Time 2 1 times n 1 2 is equal to time 1 2. And so we can then also assume the period of the two different lights. Period 2 times n 1 2 is equal to period 1. Right? So what does that mean? If you're going from higher, so the higher density has slower time. And so it has to have a shorter period to match the lower density frame. So what does that mean? When we're going from this way, periods down, frequency is the inverse of period, so frequency goes up, energy goes up. When we go this way, okay, so as we're going from lower densities to higher densities, the period must decrease to conserve time. That means that we're increasing the frequency and the energy of the photons increasing. If the photon's moving from higher densities to lower densities, its period is going to increase, the frequency is going to decrease, and its energy is going to decrease. And so to sum up, light appears to slow down in higher densities, and this is just due to the time dilation of the frames of different densities. Light wants to turn toward increasing n, and light gains energy as n increases. And so that would be my whole idea of how light gets bent by mass. Now, this brings up some weird issues, and I want to speak about two of them in particular. I guess one has two parts, so is this three? I don't know. Special relativity is a little bit weird. So this is just my little moving inertial sphere, and we have the density in here is going to be greater than out here. Now, So Einstein says that light always moves at the same speed. Well, for the local frame, but this particular experiment assumed that we can measure or see light, see in this experiment. And I'm saying that we would never be able to experience that light moving at c because we can't be in that frame unless we're distorting the frame or whatever. Plus, I also said that light slows down when density is higher. So how do we explain all of this? So what we need to remember is that light, here's the little thing, and it's really just, whatever. There's a triangle here just to show the down back path, but those would really be right on top of each other. What I'm saying is that we would experience looking at the leg, the light moving down and back is going to be going slower, but the whole inertial frame is going to be moving at velocity here. Now, Einstein says that this is equal to c. I guess he deserves a capital E. And so we see the inertial sphere moving, and the speed of light in that inertial frame is going to be moving slower. And so what's interesting, though, is if we go c12 squared plus v squared equals c squared, and I, from before, said c12 is equal to, it's going to be moving slower based off of some parameter n, right? So c squared over n squared plus v. Let's do some math. I'm going to, move this over there and that down there. So then we're going to get rid of the c squared on top. So now that's 1. This is 1 minus. So which is suspicious because this is also equal to gamma. So that's interesting. I don't know if I have anything else to say about that, but it's interesting. Now, the symmetric contraction is also kind of weird. Einstein says that there's a Lorentz contraction, or I guess Lorentz says there's a Lorentz contraction, but there's a Lorentz contraction that happens in line. Last time I said that that is just an artifact of the moving inertial, the moving body, whereas the contraction is due to the increase in density of space-time. Again, we have this little light experiment bouncing back and forth. I'm proposing that times n right, so this would be dx dy. So I'm saying that basically everything inside that sphere gets squished in both directions, which is kind of weird because as dy gets smaller, is also smaller. So you basically have light going slower and slower over smaller and smaller difference. And how does that make sense in this experiment? This thought experiment that Einstein had done before. And so let's do the same kind of thing here. Of one leg of the triangle, this is going to be D, but looking from I don't know why they always have to be humanoids. So we have observer 1 who's stationary, observer 2 who's moving. And so we are interested in the distance that is shrinking, and that is going to be D2, D21. The distance here is going to be the velocity times the time it takes for light to bounce off of one side of the mirror. And we have this apparent path, but we don't really know what that is equal to. So D21 squared plus V2. Okay, we're left with this. So no matter what, D21 is always going to be equal to the speed of light in its local frame times whatever the time it takes for that light to traverse the little distance. Now, if velocity equals 0, then D21 equals D12, right? We have no distortions. And so we would have D21 squared equals the question mark. But I just said that that equals C22 T12. And so basically, this is going to equal to some factor of T. Now, if we say that velocity goes to C, D21 is going to go to 0 because it gets shrunk. And so then we're going to have VT12, but we're going to plug the C in there. So then CT12. And so in order to complete, and so both of those agree. And so I'm going to say that the full equation, I don't know if this is legitimate math or not, but, or assumptions, who knows. So basically the distance, the long end of this triangle is going to be equal to the speed of light times the time it takes. Now we're going to do everything divided by, and so we're going to get and now I'm interested in just this little bit. Now remember, before we have to pick which frame is our dominant one. I forgot to do this, but we're going to say that T22 equals T21. So that means that T12 does not equal T11, right? So we're going to say the moving frame is our one of interest. And so based off of that, T12 is going to be equal to, right? So time, we have a slower time, well, assuming n12 is larger than 1. But for a constant T21, we're going to have more time in the stationary frame. And so looking at this here, we got D21 over T12. We're going to plug in what we just solved over here. And basically that is equal to D22 over time 22 and 12, and the distance 2 in the frame 2 and the time 2 in the frame 2 is essentially C divided by N12, which from earlier we said that was the speed of the reduced speed of light as seen from the stationary. So basically all of this to show that we can arrive at the same equation as the last one. Boy, this is supposed to be an equal sign. And this gets us back to the same equation as the previous slide to show that same time dilation, or the gamma factor, if you solve for n. So there doesn't appear to be anything super scary or wrong, assuming that all of space-time gets smashed in this inertial sphere as it speeds up. Now my last point here is GR does not predict the length change around the circumference. I said this a couple times in this video. What does that mean? Well, again, we have the density over here. In order to get towards some mass, right, the density increases. Now, if we look around a mass and we shoot light around this, we get some sort of distortion. If the density increases, especially in this region where we're really close to the mass, I am saying this length, so this would be, boy, how do I, the length of the path. So S would be the length of GR is not equal to the length of space-time particles, right? Because general relativity says that the length that it passes when it's close around is going to be unaffected, the circumference, whereas in space-time particles, if the density increases, there could be some asymmetric distortions or something. We'd have to go way into the more details, but the light traveling around this mass could actually experience a slightly longer path length than the light predicted by general relativity. Now, what does that mean? Well, if we're going through more of, a higher density of space-time particles, that might act like kind of a fiber optic kind of effect and help to pull, the light around further. Or maybe it says, well, you're experiencing more light, so it kicks it out sooner. I'm not sure. We're going to have to go into that detail, but there's going to be an error in one direction or the other if, the density of space-time particles actually increases the path that light has to follow. And this is going to be incredibly small, I suspect. So if I can run some numbers, we'll get some kind of values, but I doubt it's something you can measure with like the previous, Einstein's initial experiment, well, not his experiments, but the initial validation of general relativity where they're looking at the light deflecting around the sun. But that is just to say, and it's something to look forward to that we can look at down the road. Okay, well, that was a long episode, and hopefully we could try to shorten them up in the future. I plan to do some shorter videos at some point, maybe taking the key moments. But next time we're going to talk about frame dragging, and that will cover Michelson-Morley and the Michelson-Gale Pearson experiment. And we'll just cover some other things that might arise with an Aether model in some of the previous reasons that they were shut down. Thank you for your interest, and please comment if you have any thoughts or anything else. Thanks, and talk to you next time.